So what we're focusing on for the next little bit is predicting products for reactions. We've talked about writing the equations if you're given, the description of the reactants and products. But now we're taking it just one more little step where they give you the reactants and then you need to be able to figure out how that's going to react together. And your reaction types are really going to help you understand that. So let's start with what to look for each reaction type. This little video is only going to cover synthesis and decomposition because we get into a few more things with single replacement it'll take a little bit longer. So this is just synthesis and decomposition for now. And so for a synthesis reaction, they're really pretty easy to recognize. If you have two single elements, you know that it has to be a synthesis reaction. The only thing that can happen in that reaction is they can join up and go together. You can't break them down any further. And if they're just elements, there's nothing to really swap or replace like there is with a replacement reaction. So if you've got single elements, you know that you've got synthesis. Now that does not mean that sometimes two compounds can't combine, but you'd have to know a little more information to see that. And so if you have that happen, you're just going to combine those elements into a correct chemical formula. So it's not just as simple as putting them together, in a 1-to-1 ratio. That's why we spent time talking about writing chemical formulas, because you have to consider what's going to happen to balance out those charges. So just a couple of quick examples, won't take long. You may have something like this: sodium, metal, and chlorine react. So that tells you what your reactants are. And I can immediately say, okay, sodium, it's a metal, so it's a solid. Chlorine is a gas. If you don't know solids, liquids, and gases from the elements, some periodic tables are color-coded for solids, liquids, and gases. And so if we were in the classroom, you'd be able to see that. But that's how I know chlorine's a gas. It's a certain color on the chart. Another thing I want to point out about chlorine is I wrote it as Cl2, not just Cl. And I think probably I mentioned this when we had Chemistry 1, but I know it's been a while, so I've got to get my periodic table out here. There are 7 elements that do this. In other words, they double up instead of just being single. So sodium, it's just by itself. If it's sodium, it's Na. There's one of them. But chlorine is double. We call those diatomic. Di meaning 2. And so the way to remember that, it's going to get bumpy here, so hang on just a second. I mentioned that there are 7 of these. And if you look at the periodic table, you'll be able to see those numbers real clearly. And I go to element number 7, which is nitrogen. Then I make the number 7, so going across and then down. If you can kind of imagine that number 7 that's outlined there. Those are the ones that are diatomic. So nitrogen, if I have it in a compound nitrogen gas, it's N2. Oxygen gas is O2. Fluorine is F2. Chlorine, which is the one we're using, Cl2. Bromine, Br2. And iodine is I2. So you go to 7 and you make a 7 to find 7 of those 7 elements. But if you're really paying attention, you notice that's not 7. That's 1, 2, 3, 4, 5, 6. So I need one more. So these 6 plus 1, and element number 1 being hydrogen, is your other diatomic. So that's just something you kind of have to get in your brain. You have to remember to look for those elements that naturally are diatomic, because you'll be expected to put those into your equations that way. There's another little memory trick for those, and it's the mnemonic Honkel fiber. The breakfast of chemists, high fiber. So that gives you your 7 elements: hydrogen, oxygen, nitrogen, chlorine, fluorine, iodine, and bromine. So either way you want to think about that, just keep those in mind, and I'll keep reminding you. So anyway, if you've got a reaction like this, sodium plus chlorine, again, the only thing I can do is put them together in a compound. So I'm going to get sodium chloride, which is NaCl, and just for illustration purposes here, I know that sodium is a +1 element, chlorine is -1, so those two charges cancel out, so that's why it's 1 to 1. So you notice that this 2 does not automatically come over with the chlorine. The formula is whatever it needs to be to cancel out those charges. And then I have to go back, of course, and balance the equation to make it all work out. So sodium is balanced, chlorine is not. So I need a 2 there, and then I need to put a 2 in front of the sodium to finish balancing. So simple as that. We'll do one more. If you want to fast forward through this, if you think you got it, fast forward, no problem. So zinc oxidizes when it's exposed to oxygen in the air. Sometimes when these equations are described, you just see it say something about the air. If it's talking about the air, we're talking about the oxygen. That's probably what's going to be reacting. So same kind of thing, zinc plus oxygen. Zinc is a solid, oxygen's a gas. And they're just going to combine to make a compound. So I've got zinc oxide, and then as usual I have to look and check out my charges. So zinc is +2, oxygen is -2. Zinc is one of those, it's a transition metal there in the middle of the table, but it does have a constant charge, so that's how I know that's why it's not zinc Roman numeral 2 when I would write it. So those two cancel out again in a 1 to 1 ratio. Notice oxygen is one of my diatomic elements, it's O2, and so there's my formula. Zinc oxide is a solid. Metal and non-metal compounds are ionic. One of those characteristics is ionic compounds have very high melting and boiling points, so at room temperature it's going to be solid. Our sodium chloride would be also. And then I just need to balance it. So oxygen is the only thing out of balance, which fixes that, but messes up my zinc. And so simple reactions there. Now, decomposition reactions are the easiest ones to recognize, but there's a little more to them. There are a few things that you're going to need to kind of know for these. And I've got it all outlined for you here. So a decomposition reaction, you can always tell it's decomposition because there's only one thing as a reactant, and it has to be a compound. I can't break down an element. Now, another thing about decomposition is it often requires heating. And so it may say sodium hydrogen carbonate is heated. If it just says that with one compound and there's heat, you can be pretty sure it's going to be a decomposition reaction. Another thing that you might see with decomposition is electrolysis. That's adding energy in the form of electricity, and so don't let those things throw you off. It's just a decomposition reaction. It's just telling you what caused it to decompose. Lots of times it's heat, it could be electricity, sometimes it's even light or something like that. So again, first thing to look for is a single compound, and then if you don't know what else to do, you're going to break the compound into individual elements, especially if it's a binary compound, which is only made of two things. Or I'm giving you some special cases here to look for, and I'll give you examples of these. So metal carbonates don't break down into all of the individual elements. And so if I'm talking about a metal carbonate, remember carbonate is a polyatomic ion, it's CO3 with a -2 charge. So any metal combined with a carbonate is going to break down into the metal oxide. So whatever your metal was, it's going to join up with oxygen as the ion. Oxygen is not diatomic here when it's a in an ion, and CO2. So if you look at this, kind of makes sense. Your CO3 breaks into CO2 and an oxygen, and the oxygen stays with the metal. A metal hydroxide, so metal hydroxides are OH minus, is going to give you a metal oxide. So here again, the oxygen stays with the metal, and H2O. So your hydroxides are going to form a water molecule. And metal chlorates are ClO3 with a -1 charge. This time it's a little different. The chloride stays with the metal and oxygen gas is produced. Now there are a bunch of these special cases. I'm just asking you to kind of be on the lookout for these three, just to sort of make the point that they don't always break down into individual elements when you have a decomposition. So let's look at a couple of these. Magnesium oxide is heated strongly. So here, it's just a binary compound. So the only thing I can do with that magnesium oxide is break it into the two elements that form it. So I'm going to get magnesium metal. Since it's a metal, I'm assuming it's going to be solid. I'm assuming I haven't melted it. And oxygen is diatomic, so it has to be O2 for oxygen gas. And balance your equation. I need a 2 there and a 2 there. Moving on down. Sodium carbonate is heated over a burner flame. So that's one of my special cases. It's a metal carbonate. Sodium is your metal, and carbonate is the polyatomic ion there. So it tells me that it forms a metal oxide in CO2. So sodium oxide, think about your charges. Sodium is +1, oxide is -2. So my formula is going to be Na2O. This is an ionic compound, so it's going to be solid. Again, metal, non-metal makes it ionic. And carbon dioxide gas. The nice thing about these is, since oxygen is -2 and carbonate's -2, these will always balance out. Na2, Na2, and then your oxygen plus CO2 gives you the CO3. Real quickly, a couple more. Calcium hydroxide breaks down. So there's my metal hydroxide, CaOH2. It's ionic, so it's a solid. And that's going to give me the metal oxide plus water. So that's CaO, metal oxide, calcium's +2, oxygen's -2, and water is H2O. Liquid, could be a gas if it's heated. Don't get too bent out of shape over those things. And in this case, I believe we're balanced. Calcium's balanced, 2 oxygens and 2 hydrogens. So there's your 2 oxygens and there are your 2 hydrogens. They won't always balance. You've got to check them. And last one, got to go quick here. Excuse me. This is a metal chlorate. Potassium chlorate is heated. I'm going to get the metal chloride, which means your metal combined with the chloride ion. This is an ionic compound, so it's a solid. Potassium's group 1, so it's +1. Chloride is group 17, so it's -1. So they combine in a 1-to-1 ratio. And the other thing it tells me I get is oxygen gas. Whoops, that's a G. And then balance your equation. Start with your metal. Potassium's good. Non-metals that aren't oxygen, chlorine's good so far. Then my oxygen is out of balance. I have 3 here and 2 here. Least common multiple is 6. So I'm going to get 6 oxygens on this side if I put a coefficient of 3 in front. If I put a 2 in front here, I'm going to get 6 oxygens on this side to balance that, which of course changed my potassium and my chloride. But